am Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss the definitions and terminology involved with engineered and magnetic materials, that is module 4 in the course Applied Physics. And before seeing the definitions, let us first understand what a definition is and what terminology is and what their importance is. So first, what is a definition? The act of defining or of making something definite, distinct and clear. That is what a definition is. Or it is the formal statement of the meaning or the significance of a word or a phrase or an idiom as seen in the dictionary. And it is also a statement that expresses the essential nature of something. So that is why whenever we define a term or a definition, it has to be in appropriate terms. Now, why is the definition so important? Because it enables us to have a common understanding of the word or the subject. And they allow all of us to be on the same page when we are discussing or reading about a particular issue or a subject. That is why we have to make sure that we properly define our words and phrases so that all will understand. Now coming to terminology. What is terminology? It is the body of terms used with a particular technical application in the subject of study or profession, etc. So what is the importance of terminology? Terminology plays an important role in understanding of the context and specialized texts. And understanding the intricate terminological details of the technical and scientific context helps the students to comprehend what the main message of the text is. Not only that, it also helps specialists to transmit the content in a very effective manner. So with this, we will move on to the discussion on definitions and terminology of module 4. So let us see the brief outline of this module. The module is engineered electric and magnetic materials. So in that we have the subtopics: polarization, permittivity, dielectric constant. So these are very important terms when it comes to electric and magnetic materials. And we are going to understand what their definitions are and how do we use the terminology. Then the next one is internal field in solids and the Clausius-Mosatti equation. Then electronic, ionic and oriental polarization. Then ferroelectricity, magnetization, permeability, susceptibility, all these will come under the definitions. Then the classification of materials into dia, para and ferromagnetic on the basis of magnetic moment. And also last one is the hysteresis curve. So we will discuss the definitions related to all these topics now. So the first one, define an electric dipole. What is an electric dipole? Two equal and opposite charges separated by a distance r constitute a dipole. So how do we represent it? Suppose we are taking two charges. This is one charge and this is another charge. They are separated by a distance r. These two charges, I will name this as plus q and this is minus q, because it is mentioned they should be equal in magnitude. So I am taking them as q and q. But they are opposite charges. So if this is a positive charge, this is a negative charge. And they are separated by a distance r. And this constitutes the dipole. So if you are talking about a dipole, two equal and opposite charges separated by a distance r will constitute a dipole. Now, what is dipole moment? How do we define dipole moment? It is the product of the charge and the distance between the two charges. That is called the electric dipole moment. Whatever we have seen just now, two charges, equal and opposite charges, plus q and minus q, they are separated by a distance r. They form a dipole. Now we have to find the dipole moment, and we call it as the electric dipole moment because it is due to the electric charges. So how do we get the dipole moment? Dipole moment is denoted by mu. Mu denotes the dipole moment. It is the product of the charge. Because they are equal in magnitude, we are multiplying with one charge multiplied by the distance between the two charges. So mu is equal to q into r. So that is how we calculate the dipole moment. Now, what is polar dielectric? So the word polar is important here. The dielectrics in which the center of gravity of the negative charge distribution does not coincide with the center of the positive charge distribution, then they are called as polar dielectrics. So whenever we are taking a dielectric, there are negative charges, there are positive charges. Now, if the center of gravity of the negative charge does not coincide with the center of gravity of the positive charge, then we call them as polar dielectrics. You see the example here, we have taken the example of water, H2O. So this is one H plus, this is another H plus, so two positives, and this is O, which is minus. Now, the center of gravity of this is not coinciding with the positive charges. Then it is a polar dielectric. And this molecule will have a net dipole moment. There will be a net dipole moment in case of polar dielectrics. Now, what is a non-polar dielectric? Non-polar. So, the dielectrics in which the center of gravity of the negative charge coincides. So, that is the difference here. It coincides with the center of the positive charge distribution. Then we call them as polar dielectrics. So, these non-polar molecules, they have symmetrical nature or symmetrical structure. That is why they coincide. And the net dipole moment is 0. So, they cancel each other. So, therefore, the net dipole moment is 0. If you see examples, we have hydrogen, nitrogen, oxygen, and CO2, benzene. All these are examples for non-polar dielectrics. So, if you see in the example here, we take C and O2. Now, if you see the bond dipoles, the center of gravities are coinciding with each other. So, the overall dipole moment is 0, and we call this as non-polar molecule. Next, define dielectric constant or the relative permittivity of the medium. So, dielectric constant is the ratio of the permittivity of the medium and the permittivity of free space. So, it is denoted by epsilon r. We are using the Greek alphabet epsilon, suffix r. It denotes the relative permittivity. So, how do we write the absolute permittivity as epsilon upon epsilon naught? Epsilon r is denoting the relative permittivity or the dielectric constant. It is the ratio of permittivity of the medium. So, epsilon here denotes permittivity of the medium. It is the permittivity of medium. And epsilon naught is the permittivity of free space. It is the permittivity of free space or vacuum, we say. It is the permittivity of free space. So we are defining epsilon r as the ratio of permittivity of the medium to the permittivity of free space. So this is the formula for dielectric constant. Now what is electric polarization? What is electric polarization? So when a dielectric substance is placed in an electric field, we are placing a dielectric substance in an electric field, then what happens? The positive and the negative charges are displaced in opposite direction. And this phenomena, we call it as electric polarization. We are calling this phenomenon as electric polarization. Now, we see in the figure, we try to understand with the help of this figure. So, in the absence of an electric field, there is no electric field. This is how the charges are. They are oriented in different directions. But when a field, an electric field is applied, then what happens? These charges are displaced in opposite direction. All the negative charges are directed towards the left and all the positive charges towards the right. So this displacement of the charges gives rise to electric polarization. Next, define the term polarizability. What is polarizability? It is the ratio of the dipole moment to that of the electric field applied. So the dipole moment and the electric field applied, the ratio gives us the polarizability. So alpha is equal to alpha. Polarizability is denoted by alpha. So it is the ratio of dipole moment and the applied electric field. It is the ratio of dipole moment and the applied electric field. Dipole moment we are denoting by mu and the electric field is denoted by E. So we use the formula alpha is equal to mu by E and the units in which we measure it is farads per meter square. Next, describe polarization vector. What is a polarization vector? It is defined as the average dipole moment per unit volume of the dielectric. So when we are measuring a polarization vector, it means it is the average dipole moment per unit volume. So how do we write it? P is equal to, P represents the polarization vector. It is equal to average dipole moment upon volume. So P is equal to mu upon V. Here mu represents the average value. So P is equal to mu by V. Mu represents the average dipole moment and V represents the volume. Then recall electric susceptibility. What is susceptibility? So the electric susceptibility chi, this is also a Greek alphabet, we call it as chi, not x, this is not x. It is defined as the ratio of the polarization vector to the applied electric field. When we talk about susceptibility, it talks about the way it is the object is going to get or the dielectric is going to get electrized, I can say. So the susceptibility chi is defined as the ratio of the polarization vector to the applied electric field. So chi is equal to P upon E. So P here represents the polarization vector and E represents the electric field. So we can write chi is equal to polarization vector upon applied electric field. So this is the electric field. Now describe electronic polarization. What is electronic polarization? So when an electric field is applied on a dielectric material, then all the positive nuclei of the atoms move in the field direction and all the negative electronic cloud of atoms move in the opposite direction, and hence dipoles are formed, and that produces the dipole moment. This phenomena we are calling it as electronic polarization. So whenever we talk about an atom has a nucleus, positive nucleus at the center, and we have the electrons revolving round the nucleus in circular orbits. So we consider all this as the electron cloud and the positive nucleus at the center. Now what this says is, when an electric field is applied to a dielectric material, in a dielectric material there are n number of atoms. So in all the atoms, what happens? The positive nuclei move in the field direction. We try to understand with the help of this diagram. So if you see here, the first figure shows an atom with a positive nucleus and the electrons revolving around it. We are calling it as the electron cloud. And this is when there is no electric field that is applied. So this is the positive nucleus in an atom, and there is no electric field, and we are representing the electron cloud. But when an electric field is applied, and this is the direction of the applied field, then what happens? The positive nuclei move in the field direction. So what is happening? This positive charge is moving in the direction of the field, and all this negative cloud, this is the electron cloud, it moves in the opposite direction, and that creates a dipole moment, which gives rise to electronic polarization. Next, define a magnetic dipole. What is a magnetic? Till now what we have seen is an electric dipole. Now we are going to talk about magnetic dipole. Two equal and opposite poles separated by a distance r constitute a dipole. Now if you see a magnet, any magnet you take, I am just for convenience sake showing a bar magnet. There is a north pole and a south pole. So these are the two poles of the magnet. So if we are talking about equal and opposite poles, means opposite in nature. So this is the north pole and this is the south pole. So they are opposite to each other. They are equal, means the magnitude is equal, and they are separated by a distance r. That constitutes a dipole. Di means always two. So we are considering two equal and opposite poles. Now what is magnetic flux? It is defined as the amount of magnetic lines of force passing perpendicularly through unit area of the given material. So what are these magnetic lines of force? So whenever we have a magnet, so this is the north pole and this is the south pole, you can trace the magnetic lines of force. They always start at the north pole and end at the south pole. So this is how we have the lines of force. Okay, so we can trace them. You also have the field going like this. These are the lines of force. Now, it is the amount of magnetic lines of force passing perpendicularly through unit area of a given material. Suppose we place a dielectric material here. So, the number of lines of force that are passing perpendicularly through unit area of this material, we call it as magnetic flux. And magnetic flux is denoted by phi. We call it as phi. Recall the term intensity of magnetization. What is intensity of magnetization? So, the magnetic moment per unit volume is called the intensity of magnetization. We know what is magnetic moment. So, if we know the magnetic moment, we can calculate the intensity of magnetization. So, it is denoted by capital M. The intensity of magnetization is denoted by capital M, and it is given by the ratio, or it is the magnetic moment per unit volume. So, we are writing it as magnetic moment upon volume, and the units is amps per meter. Next, define magnetic induction. What is magnetic induction? Magnetic induction at a point is defined as the force experienced by a unit north pole placed at that point, and it is denoted by V. So, the same way we have talked about the flux. So, here what we are talking is, if you take a unit north pole and you place it in a magnetic field, so it will definitely experience a force. So, what is the force that is experienced by a unit north pole when placed at that particular point? We call it as the magnetic induction. So, to measure, what we use the formula is B is equal to phi upon A. So, the flux per unit area, that gives us the magnetic induction, which is measured in Webers per meter square. So, flux is measured in Weber. The area is measured in meter square in SI system. So, we represent it by Weber per meter square. Next, what is permeability? It is the ability of the medium to pass or to allow the magnetic lines of force through it. Means, if a material is allowing the lines to pass through it, means it is permeable. So, it talks about the ability of the medium to allow or to pass the magnetic lines of force through it. So, permeability is given by mu is equal to mu naught into mu r. So, here mu is the permeability of the medium. So, mu represents the permeability of the medium, and mu naught represents the permeability of free space or air or vacuum. When we are talking about free space, it can be air or vacuum. Then mu r represents the relative permeability of the medium. So, relative permeability means here permeability of the medium with respect to the permeability of free space. So, that is how we define permeability. Next, what is magnetic susceptibility? Magnetic susceptibility is defined as the ratio of intensity of magnetization and the applied magnetic field. It is denoted by chi. So, chi is equal to m upon h. What m denotes is the intensity of magnetization, and h here represents the applied magnetic field. So, susceptibility is given by m upon h. When we say susceptible, if you are talking about a material, how easily it can be magnetized. So, susceptibility talks about the way it can be easily magnetized. So, when chi is equal to 0, it is in vacuum. In vacuum, chi is equal to 0. And chi is positive for paramagnetic and ferromagnetic materials, because these materials can be magnetized easily. paramagnetic and ferromagnetic. But when it comes to diamagnetic materials, it is negative because we know diamagnetic materials cannot be easily magnetized. And because it is the ratio of two similar quantities, it has no units. So, chi is a dimensionless quantity. Next, define relative permeability. We have already seen the formula. What is relative permeability? It is defined as the ratio of permeability of the medium and the permeability of free space. So, from this formula, what we can write, mu r is equal to mu upon mu naught. Mu r is equal to mu upon mu naught. What is mu r? It is the relative permeability of the medium. And what is mu? It is the absolute permeability of the medium. And what is mu naught? It is the permeability of free space or vacuum. So, relative permeability is the ratio of mu to mu naught. Now, which gas is used for insulation? Nitrogen and sulfur hexafluoride, which we write it as SF6. No, it should have been SF6, are used for insulation. Now, nitrogen is used as an insulating medium, while SF6, it is used in high and medium voltage switchgears and circuit breakers. So, they are used in switchgears and circuit breakers. Next one, what is space charge polarization? What is this space charge polarization? We have already seen electronic polarization. So, what is the space charge polarization? In some materials containing two or more phases. So, if you are taking a material which has two or more than two phases, and when we apply an electric field, it causes the accumulation of charges at the interface between the phases or at the electrodes. So, we have taken a material having two phases, you imagine, and an electric field is applied. Then there will be accumulation of charges at the interface of the phases. So, because of that, there is polarization. And this type of polarization, we call it as space charge polarization. Next, mention any two breakdown mechanisms. What are breakdown mechanisms? One is intrinsic breakdown and the other one is thermal breakdown. We also have avalanche breakdown because they are asking to mention any two. We are mentioning intrinsic breakdown and thermal breakdown. We'll try to understand what is intrinsic breakdown and what is thermal breakdown. So, what is intrinsic breakdown? Now, for a dielectric, the charge displacement increases with increasing electric field strength. So, this part we have already discussed. When we take a dielectric material and we subject it to an electric field, the charges will get displaced. And as the electric field strength increases, the displacement also increases. Okay. So, if you understand this, with the increase in electric field strength, the charge displacement also increases, and beyond a critical value or a particular value of the electric field strength, there is an electric breakdown. Why there is an electric breakdown? Due to the physical deterioration of the dielectric material. Because of the displacement of the charges, there may be a physical deterioration in that dielectric material. And because of that deterioration, there may be an electric breakdown, which we are calling it as intrinsic breakdown. Next, what is thermal breakdown? As you know, thermal is always related to heat. So, how it is happening? How is thermal breakdown happening? When an electric field is applied to a dielectric medium, some amount of heat is produced, which we have not discussed before. Now, we have only talked about the charges are getting displaced and there is polarization. Now, what we are considering here, when an electric field is applied to a dielectric material, some amount of heat is produced. And as you apply the field or increase the field strength, due to excess of heat, the temperature inside the dielectric increases and it may produce local melting in the dielectric material. So the material will melt inside, and during this process, a large amount of current flows through the material and causes the dielectric breakdown. So this type of breakdown, we are calling it as thermal breakdown because it is due to the heat. What is happening? The material is melting inside, and because of this melting, there is large amount of flow of current due to the breakdown. So we are calling it as thermal breakdown. Next, what are the requirements of good insulating materials? We are talking about insulators or insulating materials. So number one, they should have high electrical resistivity. So they should resist the flow of current through them, electrical resistivity, to reduce leakage of current. So when the resistivity is more, there will be no current flow through it. So it reduces the leakage current. Next, high dielectric strength. High dielectric strength helps it to withstand higher voltages. When we are subjecting it to a high electric field, then it has to withstand. So it needs high dielectric strength. And then small dielectric losses. The losses have to be minimum and sufficient mechanical strength of the material. So all these are important characteristics of good insulating materials. Next, what is an active dielectric? We know what is a dielectric, but what is an active dielectric? A dielectric which can easily adapt itself to store electrical energy in it. That is called active dielectric. It is adapting itself to store the electrical energy. Examples are piezoelectrics and ferroelectrics. These are the examples of active dielectrics. Now, what are passive dielectrics? What are passive? So, those dielectrics which restrict the flow of electrical energy. So, it is exactly the opposite of active dielectric. So, they are restricting the flow of electrical energy. We call them as passive dielectrics. Examples: glass, mica, plastic, all these are passive. Next, what is meant by pyroelectricity? What is pyroelectricity? It exhibits creation of electronic polarization by thermal stress. So, the electronic polarization occurs due to the thermal stress. Then we call it as pyroelectricity. Next, what is optical absorption and infrared absorption in a dielectric? So, first we'll define optical absorption and then infrared absorption. So, the dielectric losses in the optical region associated with the electrons. So, if these losses are in the optical region, we call it as optical absorption. And this absorption leads to the color of the materials. When we are talking about different colors of the materials, it is all due to the optical absorption. Then, dielectric losses in infrared region associated with ionic vibration. So, in infrared region, what happens? There are ionic vibrations, and because of which there is absorption, we call it as infrared absorption. Then what are the applications of ferroelectric materials? So first, what is a ferroelectric material? A material which allows the current to pass through it very easily. They are called ferroelectric. So ferroelectric materials are used to make pressure transducers, ultrasonic transducers, microphones and gas filters. And they are also used in memory cores in computers, the greatest application. Memory cores in computers, we are using ferroelectric materials, and also to measure and control the temperature. In which materials the magnetic anisotropy is followed? What is this magnetic anisotropy? So in materials like iron, the magnetic properties depend on the direction in which they are measured. So if the direction changes, the magnetic properties change. So it all depends upon the direction in which they are measured. So we are calling it as magnetic anisotropy. And if you are talking about iron, it is a ferromagnetic material. So in ferromagnetic materials, generally we see this magnetic anisotropy. Next, which phenomenon is analogous to piezoelectric effect? So what is piezoelectric effect? It is the mechanical strain caused on a material like quartz when subjected to electric field. So if you are taking a material, a quartz material, and you apply an electric field to it, and because of this electric field, there will be a mechanical strain in this dielectric material. And if the same is observed in a ferromagnetic material, we call it as magnetostriction. So that is analogous. Piezoelectric effect, whatever we are seeing here is analogous to magnetostriction in a ferromagnetic material. Now mention the energies involved in the origin of domains in a ferromagnetic material. So the term domain is important here. So mention the energies. First, what are domains? So whenever you are talking about a material, there are different regions that are formed which can be easily magnetized, spontaneously magnetized. So this is one particular domain. This is one domain. Another, if I am taking up a magnetic material. So the question here is, what are the energies that are involved in the formation of these domains? One is the magnetostatic energy, then the crystalline energy, the domain wall energy, and also the magnetostriction energy. Magnetostatic, magnetostriction, crystalline, and domain wall. All these energies are involved in the formation of these domains. Now, what is hysteresis in magnetic materials? What is this hysteresis? The lagging of magnetic induction B behind the applied field strength. We are calling it as lagging of magnetic induction. So what we need to understand here is, if you take a magnetic material, I say a ferromagnetic material, and you apply a magnetic field to it, a field strength to it, then what happens? Slowly all the domains will be aligned in the same direction and there will be magnetism induced into it. So we call it as magnetic induction. Now, if we can trace the applied magnetic field H versus the magnetic induction, means we are taking a magnetic material and we are trying to trace how the magnetic induction is occurring with the applied magnetic field. So if you start here, as the magnetic field increases, the magnetic induction also increases. And here it reaches a saturation point, means it can no more be magnetized. Now at this point P, if we can withdraw the magnetic field that is applied, means I am removing the magnetic field, so coming in the reverse direction. You see here at this particular point, the applied field is 0 while withdrawing. So even though the applied field is 0, still there is some magnetism induced in the material. So we call it as residual magnetism. And then as you trace it back, what is it you are observing is here again, the magnetic induction becomes 0 in the negative direction. And again, in the negative direction, this is the saturation point. And as you apply the field again, so this is how the curve is traced. And we call this loop as hysteresis loop. So what this talks about is the magnetic induction B always lags behind the field strength. So when you see here, still there is a field. It is not coming to 0. It is always lagging. Where is it becoming 0? It is becoming 0 here. So what we are talking about is with the field, B is always lagging behind, which we are calling it as hysteresis. Next, what is the origin of magnetic moment in magnetic materials? How is this magnetic moment occurring? So, the magnetic moment originates from the orbital motion and the spinning motion of the electrons. So, when we see in an atom, the electrons orbit in fixed orbitals. And also the spin of the electrons also matter. When we are talking about the spin of the electrons, they have plus half and minus half. The spin and the antispin we talk about. So the spinning motion of the electrons also gives rise to the magnetic moment. Next, what are permanent magnets? Substances which at room temperature retain their ferromagnetic property for a very long time. They are called as permanent magnets. If you are taking a material, like a ferromagnetic material, an example, and if you magnetize it, and if it can retain its magnetism or its magnetic property for a longer period of time, then you call them as permanent magnets. Next question, is the steady electric current the only source of magnetic field? So what we are seeing here is the magnetic field will give rise to electric current, but is the steady field only source of magnetic field? So the other way around, when you have a current flowing through a conductor, there is magnetic field produced through it. So now, is the steady field only source of magnetic field? No. Steady current is not the only source of magnetic field. Magnets are also source of magnetic field. When you are taking magnets, you can use the magnets to produce the magnetic field. And also unsteady current also you can use, not only steady current. They will also be a source of varying magnetic field. When it is an unsteady current, you will have a varying magnetic field. Next, relative permeability of a material mu r is equal to 0.5. Identify the nature of the magnetic material and write its relation to the magnetic susceptibility. So how are we classifying the materials depending upon the relative permeability? If the value of mu r, relative permeability, is less than 1, they are diamagnetic materials. They are diamagnetic materials. If the value of mu r is just greater than 1, then they are paramagnetic materials. And if mu r is much greater than 1, then we call them as ferromagnetic materials. So this is how the magnetic property depends upon the value of mu r. So here we are given a magnetic material whose relative permeability is 0.5, means it is less than 1. So when it is less than 1, it should be a diamagnetic material. So the material here is diamagnetic material because the condition is mu r is less than 1. And what is the relationship with the magnetic susceptibility? Magnetic susceptibility is denoted by chi. So mu r is equal to 1 plus chi m. Suffix m shows the magnetic susceptibility. So this is the relationship between mu r, the permeability, and the susceptibility. Next, relative permeability of a material mu r is 400. What is mu r equal to? 400. So identify the nature of the material. So this value of mu r is much greater than 1. And so when it is much greater than 1, it is a ferromagnetic material. So the material whose relative permeability is 400 should be a ferromagnetic material. In what way is the behavior of a dielectric material different from that of a paramagnetic material when kept in an external magnetic field? So we have an external magnetic field, and in that we are placing one diamagnetic material and one paramagnetic material. So how do they behave? A diamagnetic specimen or a material is repelled by the magnet. So diamagnetic will not allow the lines of force to pass through them and it cannot be magnetized. So it is repelled by a magnet. While a paramagnetic material moves towards the magnet, it will be attracted towards the magnet. So that is the major difference when we are placing a diamagnetic as well as a paramagnetic. This is repelled and this is moving towards the magnet. Now, the paramagnetic always gets aligned along the field and the diamagnetic will be perpendicular to the field, away from the field, perpendicular to the field. Next, name two elements, one having positive susceptibility and the other having negative susceptibility. So when I said susceptibility, it all talks about the way the materials can be magnetized. If they are easily magnetized, they are susceptible to magnetism, we say. If they cannot be magnetized, they are not susceptible. So now positive susceptibility will be there for paramagnetic materials which can be magnetized. Example, aluminium and calcium. Then what is negative susceptibility? For diamagnetic materials. So dia means which cannot be magnetized. So their susceptibility will be negative. Example, bismuth and copper. They cannot be having susceptibility and their susceptibility is negative. Then the last one, what does negative susceptibility signify? We have already discussed. So negative susceptibility signifies that the material is diamagnetic in nature. So only for diamagnetic materials, we have the susceptibility chi to be negative. So this negative denotes that it is a diamagnetic material. So we will stop our discussion here and continue in the next class with the next module. Thank you and see you in the next lecture.
Like, share and subscribe. Hit the bell icon for more updates.